Of the traditional central problems of physics, there's one that we now seem to understand pretty well. That's the propagation of light through empty space. Maxwell's theory seems to tell us just about everything we need to know about that problem. Light is a wave-like disturbance in the electromagnetic field that propagates at a definite speed. Now, those are all nice words, but what do they mean? First of all, what do we mean by the electromagnetic field? Well, it's possible to detect the presence of electric and magnetic field using electric charges. If there's an electric charge in space and it feels a force, then there's an electric field present. If the charge is in motion and it feels a force due to its motion, then there's a magnetic field present. We also know what happens when the electric and magnetic fields are disturbed. A disturbance in an electric field disturbs the magnetic field, which in turn disturbs the electric field again. Energy sloshes back and forth between the two fields, and the whole disturbance propagates along at a speed which is one of the fundamental constants of nature. In principle, that disturbance can be detected in the same way that we detected the field itself, by means of an electric charge. Fortunately, we don't always have to detect disturbances in that way, because we come equipped with built-in detectors of disturbances in the electromagnetic field. They're called eyes.
An oscillating electric charge creates waves that propagate along the lines of force at the speed of light. These ripples are transverse waves in the electric field, propagating in wave fronts that become flatter and flatter farther from the source, coming more and more to resemble the plane parallel wave fronts that are called plane waves. As the wave fronts pass through each point in space, the electric field vector oscillates up and down, marking the passage of peaks and valleys of the propagating wave. Thus, an oscillating electric charge is indeed the source of outward spreading ripples in the electromagnetic field. It took James Clerk Maxwell's theory to explain the nature of light and to project the image of the electromagnetic spectrum as a whole. But for all his amazing insights, Maxwell wasn't the first to see light as a wave. According to Newton, light was made up of particles that, obeying the law of inertia, traveled through empty space in straight lines. For Newton, refraction, or the bending of light by matter, could be explained by the gravitational attraction between light and matter. However, at about the same time and on the same subject, an opposing viewpoint arose in Holland. Christian Huygens, a Dutch physicist and astronomer, theorized that rather than being composed of particles, or corpuscles as Newton called them, light was made up of waves, and in the long run, his idea would be seen as the correct one. Maxwell could show that electromagnetic waves of every frequency and wavelength would propagate through empty space at the speed of light. Maxwell's discovery, which seemed purely theoretical at the time, would lead to the sights and sounds of the 20th century, radiating through space not only as visible light, but also as radio waves, microwaves, and the entire electromagnetic spectrum. It was a discovery that would lead far beyond the Earth into the deepest reaches of space, where a wave in the intensity of the electric field implies the existence of a changing magnetic flux. That means a wave in the magnetic field. That's made possible by changing electric flux. And it's made clear only because Maxwell understood that electric and magnetic fields create each other if they move in a wave, together, at the speed of light. And so it goes, in lockstep through eternity, both fields propagating throughout the universe.